Chapter 4, Section 6, Consistent and Dependent Systems. So we're going to learn what this means. We'll determine whether a system of equations is consistent or inconsistent. We'll also understand what dependent means for a system. It would be helpful at this point if you paused and went to your desk and got yourself 3 index cards. We're going to use those before the lesson is over. We're going to start with this review of how to graph systems. I like the slope-intercept form, so if you'll indulge me, let's transform this into slope-intercept. So I will have a y-intercept of 2, so that's where we're always going to start. Right here, that's the anchor for our line. And then the slope is -1, so we're going down 1 over 1. Down 1 over 1. Let's see if I can pull this line up to appropriately graph that. That looks about right. Let's try this one. y equals -2x plus 6. And we'll simplify that to slope-intercept form. Y equals -x plus 3. So for this one, the anchor, the y-intercept, is right here. And the slope is exactly the same. So what does that tell us about these two lines? The graphs of these two equations are two parallel lines. They will never meet. So if we were thinking about a solution here, how many solutions will we have? 0. Let's try graphing this. Again, let's convert it into slope-intercept. Now, of course, it's not necessary to do that. You could do this with the y-intercept, x-intercept method, which would be very good. Divide everything through by 3. And we have a slope of -2/3. And we have a y-intercept of 4. So let's mark that right here. Here's 4. And we have -2 over 3. And that continues on and on. We could also move in this direction, back 3 and up 2, back 3 and up 2. Let me pull a line in to fit those points. Right about there, eh? Now, the second one. You probably see it. I know I do. But there really is no difference between these lines. Let me prove it to you quickly. If I divide everything here by 2, I get 2x plus 3y equals 12. So if I were to pull another line over, perhaps I should change it a little bit so we can see it's a different line. Pull this line over and put it right on there. It occupies exactly the same place. We would refer to this set as coincident lines. The graphs of these two equations are actually, these are equivalent equations, and produce graphs of coincident lines where the number of solutions you have are infinite, an infinite number of solutions, because they share every point. Back here, remember, we had parallel lines, and we had no solution because they will never touch. That's our review. Let's go on to the definitions here. This is important to mark down. A system is inconsistent when there is no solution. So if I were to go back here, this would be an example. Parallel lines, this would be an example of an inconsistent system. If a system of equations is consistent, must it have a solution? Certainly. A system of equations is either one or the other here. In other words, it either has no solution and is inconsistent, or it has at least one solution and it is consistent. So the answer is yes. Can a system of equations be both? No. The other definition we're going to study will be dependent. We'll get to that in just a moment. Determine whether these systems are consistent or inconsistent. Remember now, consistent is when there is a solution or solutions, and inconsistent is when we have no solution. Okay. So let's see what happens with this. I'm going to try to solve this using linear combination. I'll get 2x, and this will zero out. It was a nice setup, wasn't it? 6. So x equals 3. 3. And when x equals 3, I've got x plus y equals 4. So instead of writing my x, I'll write 3. So y must be 1. Well, I found a solution. So what does that tell me about this? This is consistent. There is a solution. This one, let's try it. This one's not quite as straightforward. I'm going to have to do a little multiplication. And I'll multiply this by -2. And when I do, I'll get negative 4x minus 2y equals -8. And here I'll have 4x plus 2y equals 16. Add those together. Oh! This is going to 0 and this is 0. We're going to get 0 0 plus 0, which is 0, equals 8. Since when does 0 equal 8? Not. This is an example of an inconsistent system. This tells us that there are no solutions here. The other thing that can happen, and we will see it, you've seen it in previous courses, you get something like this. When you get that kind of a result, that tells you you have an infinite number of solutions. In other words, no matter what x is, no matter what y is, it's going to be a match. You're going to have a shared point. Oh, so for linear, what would that be? Let's go back. That would be this situation here, wouldn't it? When you have coincident lines. Now, let's talk about what dependent means. A system is dependent when there are many solutions. So it's not dependent when there is one solution. Many solutions. It has to be more than one. So dependent. There are more than one solution. Can a system of equations be both consistent, and consistent means that there is a solution, and dependent, which says there are more than one solution? Why, certainly. Yeah, there's no problem there, is there? So yes to that. Can a system of equations be both consistent, that is, it has a solution, and not dependent? Well, not dependent would be either no solution or one solution, because remember, dependent says there are many solutions. So is this possible? Yes, it certainly is. Because we could have this happening. We just have one solution, and that is a consistent system, isn't it? But it is not dependent. Not dependent. Can a system of equations be both inconsistent, which means it has no solution, and dependent, having many solutions? Well, clearly not. Can a system of equations be both inconsistent, having no solution, and not dependent, not having many? That's 0 or 1. Well, yes, that could happen. So those are just some questions to make us stop and think, what does this really mean? Remember it. Dependent means many solutions. Consistent means one or more. Inconsistent means no solution. Determine whether these systems are dependent. Remember now, dependent means many solutions. So if these have no solution or one solution, they are not dependent. Let's try them out. What can we do here? You know, I'm going to do something very different. I'm going to multiply this by 1/2. Or why don't I multiply it by negative? See if I can get a negative in there. I'll multiply it by a negative 1/2. Negative 1/2. So I'm not going to do anything to the first equation. Leave it as it is. And I think you'll see the wisdom of what I'm doing. Multiplying by a negative is going to change the sign, and multiplying by half will make this a negative 4x, a positive 5y, and a negative 3. When I add those together, I get 0 and 0, adding up to 0. I add these up, negative 1. Well, this is a strange result. We know that this is impossible, and we know that this is an indication that we have no solution. So, is this a dependent system? Remember? The answer is not dependent. Clearly. How about this one? Here we have, oh, I'm so glad of this. We need a little more practice with this. Now we're going to get it. I'm going to start this off by trying to eliminate x. So I'll take equations 1 and 2, this one and this one. I'll multiply the second one by a negative 1. Then I will have x plus y plus z equals 1, and negative x minus 2y minus 2z equals negative 3, right? Just multiply all of this by negative 1. When I add these together, let's see what happens. I end up with a 0, which is what I wanted, a negative y, a negative z, all equal to negative 2. So let me write that up here. Negative y, negative z equals negative 2. Because I'm going to be using that for my second pass on this. Now I've used this one and this one. I need to use this one here. I think I'll still use the first one, and now I'll use that third one. I'm going to multiply this first one this time. Remember, I'm trying to get rid of x by negative 2. So I'll have negative 2x, negative 2y, negative 2z. I like this kind of multiplication. It's very easy to do. Equals a negative 2. Negative 2. All right. The third equation is just going to be used as is. And now we add these together. This will 0. I'll have a positive 1y, a positive z, and this is a negative 2 and a positive 4, so I'll have 2. So the equation up here will be y plus z equals 2. I'm going to add those together. And when I do, what happens? This will 0, this will 0. And this zeros. Oh, I'm happy about this. Here's a great example of infinite solutions. Wow, I guess that qualifies, doesn't it? That is certainly many. So this is dependent. Now I told you to have some index cards handy. This would be the time to get them out. We know that a 3-variable first-order equation, when we graph it, it's going to be a plane. So each of those index cards, if you imagine that they actually don't have any edges, the edges just go on and on forever, you can visualize how they would graph in space. How would we describe a point associated with this? It would be ordered triples, X, Y, and Z. So a system of three variable first order equations is a system of three planes. Okay? So a three variable equation is a plane. You put three of them together, you've got three planes. So you've got your three index cards. Hold these cards, two of them, so that they meet right along an edge. What do the points of intersection represent? If you were going to say what this is, what would you say this point of intersection is? That's right. It's a line. How many ordered triples normally satisfy a system of two equations in three variables? How many ordered triples normally satisfy a system of two equations in three variables? Well, looking at this, if it's a line, we know lines go on to negative infinity and positive infinity, don't they? So if we just have two equations in three variables, we have an infinite number of solutions. Well, normally. We can find an exception to that. We'll talk about that in a minute. Now take the third index card. Hold it so that its corner touches the line of intersection of the other two. So you have this interesting point right here. Right here, where the line of intersection between two of the cards, the line of intersection between another two of the cards, and your original line of intersection all meet together in one point. Why do you suppose that a system of three linear equations in three variables has a unique solution, whereas a system with only two does not? Remember, a system with only two had an infinite number of solutions. Just looking at this, it kind of gives us the answer, doesn't it? Now we have a third plane, and it does share an infinite number of solutions with each of the other two cards, but not with the other two cards and itself, not all three of them. The only point that all three of them share is right here, where those three lines of intersection come together. Hold the three cards in such a way that they intersect an infinite number of points. Yeah, it's possible to make these three planes intersect in such a way that we do have an infinite number of solutions. There are at least two ways to do this. And if it happens, the three equations are said to be dependent, having many solutions. This one was not dependent. It only had one solution. But if it has many, it's dependent. Hold the three cards in such a way that there are no points common to all three. Yes, if you put together a little tent shape here, you'll see that, okay, red and yellow have an infinite number of points in common. Yellow and green also, and green and pink also. But there is not a single point that all three of them share together. There are other ways you could do this. When this happens, we have no solution, now we have an inconsistent system. So just to review our definitions. Inconsistent when there's no solution. If a system of equations is consistent, must it have a solution? Didn't we see this before? Can a system of equations be both? We certainly saw this before. This is a little review. A system is dependent when there are many solutions. From what you observed, can you conclude the following? A system of three linear equations in three variables always, that's a key word, isn't it, has a unique solution. From what you observed, would this be a proper conclusion? Well, it happened here, didn't it? But we didn't get a unique solution here. We got an infinite number. And in this case, there was no solution. So, no, that would not be a good solution. That would not be a good conclusion. See you back in class with your practiced knowledge of what is inconsistent, remember that's no solution, and what is dependent when we talk about systems of equations. This is when we have many.